Okay, continuation on limits. So this part is asking us, what is the value at a? So it's asking, what is the y value when x is a? And that would be 2, right here. But we're going to say on this one that the limit does not exist because the left side is coming up to 2, it's approaching 2, but the right side is coming up and going up to infinity. 2 and infinity are not the same thing. This part's asking us, what is the y value when x is a? That's right here. Well, this looks like it's going down to infinity, and it looks like there's an asymptote here. So we're going to say that it's undefined. There is no value for a. This is an asymptote. But the limit, if this side's going down, this side's going down, so our limit is negative infinity. Both of them are going down to negative infinity. Okay, the next page in our notes is right here. Finding limits algebraically and graphically. So, when we're going algebraically, our first option is to just straight up plug in the number. See if it exists. Now, let me go back to this real quick. The value itself at a does not have to exist for us to have a limit there. For example, the value where we actually would plug in the number would give us 1, but our limit is 2. Same thing here. The value of a actually doesn't exist. However, the limit is negative infinity. So it does not have to exist to have a limit. But if it does exist, then hopefully that's the limit as long as our graph is continuous. So let's plug in a 2. 2 squared minus 2 plus 1. 4 minus 2 plus 1. 2 plus 1. Our limit's 3. And we know exactly what this looks like. This is just a parabola. So it must have the point 2, 3. So we have some kind of parabola, something like this, at 2, 3. There's our dot. What about this one? Fractions, oh, I get nervous sometimes, so let's see. 2 times 1 plus 1 over 3 times 1 minus 2. 2 times 1 is 2, plus 1 is 3. 3 times 1 is 3, minus 2 is 1. So that's 3 again. Let's look at the next one. Limit as x approaches 1. So let's plug it in. 10 times 1 minus 1. 10 minus 1. Square root of 9, it's 3. All these have a limit of 3. All we had to do was plug in 3. We had no plug in a 2, plug in a 1, plug in a 1. We had no problems. We got 3 out. So we would write it like this. The limit as x approaches 1 equals 3. All right, let's see what's in store for us now. Let's make it a little more tough. So now we want the limit as x approaches 1, and we're going to plug in a 1 everywhere we see an x. 1 squared minus 1 minus 2. 1 minus 2. Okay? 1 squared is 1, and 1 minus 1 is 0. 0 minus 2 is negative 2. 1 minus 2 is negative 1, so that means my limit is 2. All right, you'll notice that the next problem is the exact same, except we're evaluating at, or we're finding a limit at a different number. This time it's 2. So 2 squared minus 2 over 2 minus 2. Well, isn't that lovely? All right, so 2 squared is 4, and 4 minus 2 is 0. 2 minus 2 is also 0. This is called the indeterminate form, so I'm not actually going to circle that at all because that's not my answer. If I actually think back to what I know about rational functions, plugging in a 2 gives me an undefined right here. I have a whole. So I'm going to factor the numerator, what multiplies to negative 2 but adds to negative 1, negative 2, and positive 1. I also have a negative 2 in the denominator. That makes a whole. Now I can plug in a 2, and 2 plus 1 is 3. So if I were to graph this on my calculator, I would actually see a straight line like this, and at the point 2, 3, I would have a hole. I'd also have the point 1, 2, I know from the previous. So what this means is I'm not actually defined at 2, because when I plug in 2, I get this indeterminate form. So what I have to do is factor and cancel, and then plug in my 2 to what I'm left with. And I can always check this in the calculator. I can always graph this function and look at what it should be right here. Now you're going to see a little, or you're not actually going to see a little gap on the calculator, but if you do go to the table, it's going to say undefined right here. That doesn't mean that the limit doesn't exist. As I'm coming up, I'm getting closer to 3. As I'm coming down, I'm getting closer to 3. Do I ever actually hit 3? No, and that doesn't matter. That's not what a limit is. A limit is what it's getting close to. Okay, next one. So on this one, again, if I plug in a 4, I get the indeterminate form. So I have the square root of plugging in a 4, square root of 4 minus 2 over 4 minus 4. That's 2 minus 2, that's 0, and that's 4 minus 4, that's 0. Again, indeterminate form. But if you're looking at this one, you're like, Miss Baker, it doesn't factor. What do I do? You're right, it doesn't factor. We have to use a different technique on this one. And what we're going to use is something called the conjugate. And we've seen this before when we were doing simplifying trig expressions. You didn't like it, but it's back. What this does is it gets rid of the square root in the numerator. So we're going to FOIL this numerator. Oh, by the way I get the conjugate is taking the part with the square root and changing the sign to a positive. This fraction that I just wrote in green is equal to 1. So really I'm not changing it at all. I'm not changing the value of this function. I'm just changing the way that it looks because I'm multiplying by 1 and 1 does nothing. So I'm going to FOIL this numerator. Square root of x times square root of x is x. The outside is 2 square root of x. The inside's negative 2 square root of x. Those cancel out. And I'm left with negative 2 times positive 2, which is negative 4. Look what's in my denominator. Now plug in a 4. 1 over square root of 4 plus 2. 1 over 2 plus 2. 1/4. So there's something going on here at 4. There really isn't a value at 4. I know that because of the indeterminate form. There's something else going on there. But from the left and from the right, I'm getting close to 1/4. This next one's super easy. The numerator is a difference of squares. X squared minus 9 factors into x minus 3, x plus 3. My denominator's x plus 3. Cancel, cancel. Now I can plug in my negative 3, and negative 3 minus negative 3 is negative 6. So what this is saying is exactly at negative 6, no, I don't have a value. I'm sorry, at negative 3. The point negative 3, negative 6 is not on my graph. It's not there. There's a hole there. I know that because this cancels. Numerator and denominator cancels. That means there's a hole. But it would look like this. And at negative 3, negative 6 down there, there would be a little hole. So what this limit means is, as I trace this graph from the right, and I get closer and closer and closer down here, I'm basically going to get negative 3, negative 6. I get almost that. And as I come up from here, I'm approaching negative 3, negative 6. But I never actually touch negative 3, negative 6. That's a hole. But as I come from here, I'm getting close. As I'm coming there, I'm getting close. So I'm guessing we're going to get indeterminate form if I plug this in, but let's check. Negative 3 squared is 9, and 9 minus 9 is 0. Okay, got half of indeterminate form. 2 times negative 3 squared. Well, negative 3 squared is 9, and 2 times 9 is 18. 7 times negative 3 is negative 21, plus 3, yep, that's 0 over 0 again. So I'm going to need to factor this. Numerator's that difference of squares, x minus 3x plus 3. And denominator, let's see, 2x and x, 3 and 1. There we go. Cancel, cancel. Let's see, plugging in a negative 3. Negative 3 minus 3 is negative 6. 2 times negative 3 is negative 6 plus 1 is negative 5. So 6 over 5. So again, there's a hole. If I were to graph this, this one actually would have, if you remember from rationals, this one would have a vertical asymptote at negative half from this denominator. It would have an x-intercept at 3, so it looks something like this, probably. No, it has a horizontal at 1/2 because of here. So it's looking like that and like that. And this means that there's a hole at negative 3, 6 over 5. So somewhere right there, there's a little hole there. But we're looking at the graph overall, like the trend of it. It's getting close and it's getting close. It doesn't matter that it's not defined there. I'm asking, what is the graph overall doing? Should it be passing through there if it was defined? Absolutely. Okay, this last one, again, if you plug in a 9, you're going to get 0 over 0, which is indeterminate form. That does not mean that the limit doesn't exist. That does not mean that the limit is 0. It means you have to do more work. Multiply by that conjugate again. FOIL that numerator. Square root of x times square root of x is x. Your outside's 3 root x, your inside's negative 3 root x. Those cancel. Then negative 3 times positive 3 is negative 9. And what do you know? There's a negative x minus 9 in the denominator. How weird. Plugging in your 9 now. 1 over square root of 9 plus 3. 1 over 3 plus 3 is a 6. All right, let's go to the easy stuff. Let's look at the graph. I like these better. Oh my, we've got a little bit mess here. So we have a hole, we have a jump discontinuity, we have a little gap in here, then we've got another hole, and we've got kind of this like little parabola shape over here. So let's see. I better zoom out so I can actually see what they're asking. And it's too far, so now I can't see it all. I just have to keep going back up and down. Okay, we want the limit as x approaches negative 3. So the first thing that we need to know is it has to be going to the same place from both sides. It's not defined at negative 3. I have a hole there. That's all right. That doesn't matter. I'm coming up to here and up to here. That's coming to the same spot. Where is it coming to? Positive 3. That's our limit. What about negative 1? So let's look at it. Let's go to negative 1. Nope, we're going to 2 different spots, here and here. That doesn't exist. The limit does not exist. Let's look at negative 1 from the positive side, though. So just coming from the right, what are we getting close to? 2? What about 5 from the left? So go to 5, go to the left. What are we coming up to? 6. That's the limit. What about 0? There's no plus or minus up here, so we're just saying 0 overall.